Hi, we're Thursday's group analyzing the mass spring dampener. This is Sam, and this is Shannon, and my name is Kelsey. So today I'm going to talk about the objective of our project, and our objective was to analyze like a black box circuit of a mass spring dampener and a quadrature encoder. We did this by creating first a code to drive the motor, which created a signal to our rotating quadrature encoder. And then we built a decoder circuit that would turn the signal that we got into a sine wave.
So the theory behind our circuit is a little bit complicated and long, so please bear with me as we go through this. But thankfully, as Mr. Metz often does, it is broken down into subsystems, and so we can tackle each one of those one by one. The first thing, as Kelsey mentioned, was the signal that we put onto a microcontroller, which drove our motor. We've got some code that we have run into this, which allows us to determine a frequency signal that we want to send into our motor. It's driven with an H-bridge circuit, as was done in a lab previous to this. It uses 12 volts, and whenever I hit this button right here, our terminal will ask us for a frequency. This is the screen where we monitor and record all of our information. The second part of our circuit is the actual motor itself. As you can see, we run wires from our microcontroller through our H-bridge circuit into the actual motor itself, which drives it forward and backward at the frequency which we've determined. The significant bit of this motor is we actually have the spring right here running down, which hangs in suspension, what's called a quadrature encoder, which is a rotating disc with dark and light patches that stops and allows to pass infrared frequencies through infrared LEDs to what is essentially a infrared LDR, as we've analyzed before, but is what is actually a kind of transistor. The most complicated part of our circuit is the circuit which decodes the physical signal sent by the quadrature encoder into a digital signal, which we can turn into a sine wave through some code on a microcontroller. This is the circuit that does it. What we have is these two LDR/transistors that were discussed earlier are placed in series with a large resistor along a 5-volt path, so it goes from 5 volts to a resistor to the transistor to ground. And when the resistance increases and decreases across these transistors, we run a wire from in between the large resistor and the transistor into a comparator right here, which was done using an experiment prior to this. And it will pass high and low voltages. And we can determine what is a high and low voltage with this turn pot right here, calibrated directly to allow high frequencies to be designated as an on with our comparator, and low frequencies to be designated as an off. So this turns essentially small fluctuations in voltage into an on and off square wave. And here's a picture of that decoding circuit I was mumbling about just a second ago. These on and off signals from the comparator are then sent to this microcontroller, which understands which signal comes first and which signal turns off first, and therefore it can determine the direction in which the quadrature encoder is spinning. Depending on the speed of the quadrature encoder, will give us a higher value in the sine wave or a lower value in the sine wave, which allows us to create a sine wave with phase and magnitude very similar to the sine wave that we are putting into our motor initially, and then we can compare those two sine waves.
In our first subsystem, we have the microcontroller, which sends signals to the H-bridge. And connected to the H-bridge is our motor from our mass spring dampener. Our second subsystem includes our infrared LEDs, our transistors, as well as our trim pot and our LM324 chip. We have our set resistors we found by using different we tested different resistors to produce the best wave. And finally, we have our output, which we used another microcontroller, which takes the outputs of the LM324 and from the square wave, as mentioned in the theory, we can produce a sine wave.
Hi, so I'm actually going to give you a little demo of what we were doing here today. So basically, what's going to happen is right here, there's a reset button, which I'm actually going to press, and once I press that, then Shannon over here is going to enter a frequency of 0.5 hertz, which is actually going to go to our motor, and it's going to turn our motor on and kind of like make it rotate, which will then drive our quadrature encoder to also rotate and give us a signal that then will output from this microcontroller. This microcontroller will then give us a sine wave on the oscilloscope. You might not be able to see it very well, but we will be giving a live demo in class today. You should be able to see better on that. Okay, so here we go. Okay, as you can see, the blue wave has started to turn, and then we have the phase shift to make the yellow wave give you the sine wave.
One of the biggest obstacles we had to overcome in this experiment was creating large enough sine waves from the potential difference change across the transistors that we used. When we finally found a way to maximize this sine wave, here is a graph of the turn pot against the voltage out of the transistor. Once we had large enough signals to run into our comparator, we were able to create this graph, which is two phase shifted signals, where the relationship between the two, the yellow and the blue lines, determine to the microcontroller what direction and what speed the quadrature encoder is spinning. And finally, we have our actual input and output signals. The blue line is the input signal coming off of the first microcontroller. It's standardized to 5 volts, and the one that we're showing right here has a frequency of 0.5 hertz. The yellow line is the one created by decoding the quadrature encoder, and it has a similar frequency and a amplitude of much less. And here are the final two Bode plots. Unfortunately, because of friction and other actual physical phenomena, we were not able to take more data points than just 3 at 0.25, 0.5, and 0.75 hertz. However, in constructing these, we assume our filter to be a band pass filter.
To conclude things, this project went fairly well. We had a couple issues with the resistors going into the transistors. We wanted to optimize the sine wave we were producing, so we wanted to increase the resistance. So we did that, and once we did that, we noticed a lot better wave. A couple other mistakes were just burning out like LEDs and stuff, and since we used a lot smaller resistance than what we should have. But all in all, it went very well. We learned a lot, and we learned a lot about quadrature encoders and just how the mass spring dampener works in general.